vector functions. Finally, some calculus. Okay, so the definition of the derivative of a vector function will look very familiar to you. Did press record, didn't I? Yes, I did. And the microphone's plugged in. Good. Right. Okay. Definition of the derivative. Let me put that back on laptop. Is dr by dt, which we can also write as r dash of t, is the limit as h tends to 0 of r of t plus h minus r of t over h if this limit exists, which is always the small print for any limit, any definition, any derivative definition. Okay, very familiar there? Okay, that's all very well, but we'd like to kind of actually be able to calculate answers without doing them from first principles. So it turns out that if r of t is f of t, g of t, h of t, then we can slowly and ponderously work out that r dash of t is in fact simply f dash, g dash, h dash. Okay. Did I put that into here? No, I didn't. Okay, I'm not going to go into the details there. It's a very simple proof. It just takes a few minutes, and I'd rather use those few minutes for something else. So basically, if you have a vector function and you want to differentiate it, all you need to do is differentiate the component functions, which is very convenient and easy and obvious. The things that are obvious in maths are not, in fact, always the things that are true in maths. But in this case, it seems obvious that you differentiate the component functions, and that is, in fact, true. And it's very, very easy. Yay, something easy. I'm going to demonstrate with exercise 37. 37? Yes, 37. If r of t equals t, ln t, and 1 over t, then work out r of 1, r dash of 1, and r double dash of 1. Well, let's work out r dash of t. R dash of t will be 1 over t minus 1 over t squared. You simply differentiate each of the component functions. And then the double dash would be 0 minus 1 over t squared, and that would be what? That would be 2 over t cubed. And so r of 1 would simply be 1, 0, 1. R dash of 1, oops, that should be a 1, will be what? 1, 1, minus 1, and r double dash will be 0, minus 1, and 2. Okay. So it's frequently convenient when you're dealing with vector functions to think of a space curve as being the path that a particle takes as it travels through space. And if we do that, then this would be, then r of 1 would be the position of a particle, let me say the particle, because we're just assuming one particle traveling along a curve, of the particle at time equals 1. Okay. R dash of 1 would be its velocity. So velocity of the particle. Particle. At t equals 1. And then, unsurprisingly, r double dash is the acceleration. Acceleration of the particle, I keep writing particle incorrectly, at t equals 1. Let me fix that. Okay, if you drew that on a picture, you'd have some space curve that your particle is traveling along, and at t equals 1, let's say your particle is over there where that dot is. Then that is the vector r of 1. Okay? It's an arrow going from the origin to the dot. Okay? That would be the velocity, and that would be r dash of 1. It would point in the exactly opposite direction if the particle were traveling the other way along the curve. And then r double dash, so r and r dash we can actually draw on our picture very accurately. R double dash we'd have to know some information for, I suppose in our particular example. Oh, by the way, that squiggly curve is not a picture of the actual example here. That was just me, I'm just drawing a squiggle. For any given squiggle, you'd need to know some information in order to know where r double dash is pointing, because is our particle actually accelerating or is it decelerating? Oh, sorry, beg your pardon. Physics, we don't use deceleration, do we? Is its acceleration positive or is its acceleration negative? We won't know without further information, but just for the sake of our picture, let me draw r double dash in this direction just so we can have it somewhere on the picture. This r is not the r above. Sorry, it's just a random squiggle that I've drawn. So your displacement vector points from the origin to the point. Your velocity vector points tangential to your curve. And your acceleration vector points in the direction that's indicative of the acceleration, and you'd need to have some information. If somebody just gave you a picture, that's not enough for you to know. You could draw r and r dash without information, but not r double dash. That's kind of hidden information. Okay, all right. Differentiating vector functions, very easy. Question?
The actual tangential thingy.
Yeah?
Is that the row of those numbers that you get, the coordinates?
Yeah, if I'm following you, in our example above, r dash of 1 was 1, 1, minus 1, and those would be the components of that red vector, yes. Yeah.
From the actual particle?
From the actual particle, yeah. And then when your particle's at a different point in space, its velocity is going to be different. There's a potential, of course, that its velocity magnitude is the same, but at a different point in the curve, its direction will definitely be different, and hence the vector that describes it will be different. So you get a different r dash depending on where you are on your curve. And so the numbers in the brackets over there indicate the actual components of the vector. Okay, all right, and that's that. So now we're going to actually use that information to work out tangent line equations. Let me go back to my dark blue. There we go. Oh, on the topic, if you could please keep quiet, of test and exam questions, it's fairly typical, if you look through old papers you'll see, it's fairly typical for the first question or one of the early questions in a test to have A, B, C, D, E, F, and have a whole bunch of little questions about a system, where the system will be maybe two surfaces and a curve, or a curve and a surface, and then a bunch of questions like where does the curve intersect the surface, or describe three surfaces that the curve is on, or work out the tangent line to the curve at a particular point. And the very next thing we're going to be doing after this is arc length, and then there could be an arc length question. So on the topic of are these questions here typical exam questions, of the stuff that we've been doing so far, they are frequently sort of sub-questions, like an A or a B or a C of a big question, where each will be worth like 2 marks or 3 marks. Okay. So one of those typical A, B, C questions would be find a tangent line, which is what we're about to do. So let's have a look. What wise words do I have about tangent lines? Oh, hold on, there's differentiation rules. Yes, I should give you the differentiation rules, shouldn't I? Let's do tangent lines first, and then I'll give you differentiation rules, seeing as I've already done the heading. Okay, tangent lines to space curves. A line equation so Okay, so that would be a typical line equation. Direction vector, there we go. So in order to get a line equation, you need a point and you need a direction vector. In the context of vector functions, you'll get your point with your r of t, and you'll get your direction vector from your r dash of t. So, comes from r at some, usually at some specified t value, so I'm calling it t naught, and this comes from r dash at the same specified parameter value. Okay, and there's really nothing more to say except to demonstrate. So I'm going to demonstrate with exercise 38A in fact. I'm going to do 38A and then you're going to do 38B. Given the curve described parametrically by r of t equals 2t, 3t squared, 1 minus t, find the equation of the tangent line to C at the point. I've been given a point. Now the point is useful information, but it's not the most useful information for the purposes that I'm going to require. R dash of t is going to be 2, 6t minus 1. And now r and r dash and r double dash and r however number of dashes is a function of t. Okay, r is a function of t, which means the thing that you plug into it will be a value of t. It won't be a point. Okay, it'll be the parameter value that corresponds to that point. So we're going to have to figure out what parameter value corresponds to that point minus 232. And it would be in other words, what value of t, when we plug it into r of t, will give us that point? Minus 1. Because r of minus 1 equals 2, 3, 2. Okay. Okay, sometimes it takes a little bit of thinking, other times it's pretty obvious, but minus 1 is what we want. So our direction vector of our tangent line will be r dash of minus 1. And so my tangent line is x of lambda, or you can call it whatever. You can even use t as your parameter again, but I prefer to use a different parameter. Oh, minus 2. We've been given the point, that was nice, we were given sort of a freebie. There you go, and there's our tangent line. Easy, isn't it? Some stuff in life is very easy. You give it a go. 38B. If you could please be quiet. Okay, we're carrying on. Okay. I want you to move on to integrating vector functions now, but before that, let me just close up by giving the sort of the admin, almost as it were, of differentiation, which is differentiation rules, and an interesting fact or two. So, differentiation rules. There's some stuff that you can do, and there's some stuff you can't do. You'll have seen a very similar list when you did single variable differentiation back in, or I suppose I should say, real valued function differentiation back in first year. But here it is. Suppose u and v are differentiable vector functions. C is a scalar. In this case, that means real number. And f is a real valued function. Then, okay, hold on, there's going to be a page jump. There we go. Then we have a list of differentiation rules, but they're not going to startle you or surprise you in any way because they bear a very strong resemblance to their real valued function counterparts. d by dt of u of t plus v of t Okay, so the derivative of a sum is the sum of the derivatives, which you are used to. If you take a vector function and multiply it by a real number, then you differentiate the function and the real number just kind of comes along for the ride. Same as in real valued functions. Number 3, what have I got here? Okay, I've got, what is this? There's 2 different versions of the, no, in fact 3 different versions of the product rule. Because of course in vectors there are 2 different kinds of products, and by the fact that I'm considering vector function as well as real valued functions, we actually end up with essentially 3 kinds of products. So if you take the real valued function and you multiply it with a vector function, you end up with the old familiar product rule. Okay, that's nice. What if the 2 functions were actually vector functions and the product was a dot product? Well, working from first principles and doing quite a lot of hard labor, you can determine that in fact you still get the good old-fashioned product rule, where the product in question remains the dot product. Make sure I'm putting all the dashes in the right places here and all the arrows on top of the right things. Looking good so far. Okay, well, what if the product were the cross product? Now, all of these rules weren't just whispered in our ears by the angels. These rules all come from sort of definitions. They come from the definition of the derivative, the definition of the cross product, etc. So someone has sat down and actually worked through this from first principles, but hooray that they've determined that in fact you still get the good old-fashioned product rule. So it doesn't really matter what form of product you have. The product rule still applies for differentiating vector functions, which is a great comfort to us all. Yes, question.
You said the product is so far, but you put the cross in this. I mean that we still do the cross product between the vector and scalar there from that.
It's not a cross product between a vector and a scalar. All of those are vectors, because the derivative of a vector is still a vector.
You do the cross product between 2 vectors then?
Yes.
The cross product between
Yes,
two vectors.
yes. So the product rule applies, but whatever the incoming product type was, dot or cross is the same as what you end up with, if that makes sense. If you started with dots, you end with dots. If you start with crosses, you end with crosses. Okay, and then this over here, that's a composite function. It's u of f of t. That, of course, means chain rule. And chain rule also still applies, where you differentiate your outside function and then you multiply by the derivative of the inside function. So this is chain rule, and all 3 of these are product rule. The bottom line is, all the things that you used to be able to do with differentiation, you can still do. Okay, then there's one little fact that comes in useful in other places. There's no quite comfortable place to put it. I'm just going to put it here. Given a vector function r of t, we can find r of a and r dash of a at t equals a. Okay, for some t. R of a and r dash of a are not, in general, orthogonal. And you can picture that. Given some squiggly curve, put a dot on the curve, draw an arrow from the origin to the dot, draw a tangential arrow to your curve, what are the chances that those two arrows are going to be orthogonal? And sometimes they will be and sometimes they won't be. In general, they will not be orthogonal except when r of t is constant in magnitude. In other words, the modulus of r of t is some constant. Okay, and the sort of quintessential example of that is a circle. Imagine that your space curve is in fact a very boring space curve and it's actually just a circle drawn on the xy plane centered on the origin. Or in fact, centered on the z-axis really. Okay, not necessarily on the origin, but a nice circle centered on the origin. Let's just picture that. Then your arrow pointing from your origin to your dot. So if your dot is just moving around and around that curve, then your R arrow will just go round and round and round. It'll change direction, but it won't change magnitude because its magnitude will always be the radius of your circle. And we know from circle geometry in school that in circles, your tangent and your radius are always orthogonal to one another. So that would be a prime example of R and R dash being orthogonal to one another. There are other cases, but that is a very easy one to picture. Question?
For rule number 6, do we ever have a thing where it's a vector in a vector?
No, you wouldn't have a vector of a vector. Certainly not in the context of what we're doing in this course. So so that's rule number 6. It will be a vector of a scalar function. I think what I did was I was in a hurry to draw the dash and I ended up drawing it inside the bracket. Thank you. Thank you. Okay, so that's just a little fact. There was no quite comfortable place to put it, so I'll just put it there. And that can come in useful. Where is it that it comes in useful? It comes in useful when we do the normal vectors and the unit tangent vector. I'll remind you when we get there. I'll say, remember how we said this thing, and here's the thing. Okay, all right, we're making great progress. Let's move on to integrating vector functions. Also very easy, everybody keep calm. Okay, please keep quiet. So this is kind of just a little thing of interest that I'm telling you here. It in fact is not a core. We're not going to see this very often at all. We do a lot of integrating in this course, but not usually of vector functions. But I just, for completeness, if we're differentiating vector functions, what does it look like? If we're integrating vector functions, what does it look like? So I'm giving it to you almost just for completeness, but the differentiating vector functions is huge and we'll do a lot of it, but this very little. Okay, this is the fundamental theorem of calculus for vector functions. Okay, right. So what all of that is saying, that first line there is saying if you want to integrate a vector function, if you want to do a definite integral of a vector function, then you just need to do that same definite integral of all the component functions. And then that last thing is the fundamental theorem of calculus, which hopefully you recognize. If you don't recognize, go look it up in your textbook. Okay, but I don't want you freaking out about any of that. It's really not that big a deal. If you come out of this lecture reeling and thinking, oh my goodness, I only have space in my brain for a small amount of that information, make it the R- stuff, not this. And I will demonstrate with a very rapid example, and then we'll move on and probably not see it again. Exercise 42. I do tend to leap ahead, don't I? That's because in between there are TUT questions and the occasional homework question. But I realize it can be a little bit alarming. Sometimes it's like, we were only just beginning the 30s. What just happened? R of t equals. You can do this. Others have done it before you. You can do it. It says evaluate. So there's my R. It says evaluate the integral from 0 to pi over 2. Whoops, a daisy. Pi over 2 of R of t dt. Okay. Not hard. Not hard. So I'll just work out these individual derivatives. Integrals. You'll remember how to integrate, right? Particularly as you spent last week doing the revision worksheet, right? And that had a whole bunch of integration, so you're feeling all fresh and knowledgeable about integration. You did all do the revision worksheet, right? It was part of last week's TUT. You took it very seriously, right? Of course you did. Okay, so you ask yourself, what did I differentiate to get cos t? And the answer is sine t. What did I differentiate to get sine t? The answer is minus cos t. And what did I differentiate to get t? And it's a half t squared. Okay, so that would be 1 minus 0, which is 1. That would be 0 plus 1, because it's minus minus, so it's 1. And that would be pi squared over 4, pi squared over 8. Right, unless I've done something careless, that's the right answer. And according to my clock, we have 3 minutes left. I wouldn't want you to get bored. Okay. All right, what have we done this lecture? We've basically done tangent lines. Tangent lines is the core thing that we've done. Tangent lines. Given a vector field, not vector field, I beg your pardon, a vector function, how do you differentiate it? Okay, r dash and r double dash can be interpreted as velocity and acceleration, and then we can use that velocity vector to get a tangent line equation. That's the core thing we've done. The integration is a fringe thing. It's not really a core thing. And the next thing we're going to do is arc length. So I tell you what, I'm going to spend these 3 minutes talking about arc length, and that'll allow us on Monday to jump into some writing, which I will do rapidly and won't do a lot of chit-chat. Okay. So arc length, you've already done arc length, okay? You've done arc length in first year, where you worked out, given a curve, can we work out the length of the piece of curve from one spot to another spot? And that's exactly what we're going to be doing now, except the curve now will not be a curve drawn flat on an XY plane. It will now be a piece of space curve. But we're going to be using the exact same arc length formula. Now, I won't actually call you on it. Okay, so I suppose you could lie if you wanted to. Who of you remembers that you ever did arc length ever? Okay, good, right. Who thinks that if you were really pushed, you could remember the formula? Okay, all right. It's a subset. Okay, all right, but no, there's still some. Okay, who of you think? Shush. Please be quiet. I can guarantee that when you derived that formula, you went via the parametric form to the Cartesian form. So I know you will have seen the parametric form even if you never used it. Who of you think that if pushed, you could remember the parametric form of the arc length formula? And by parametric, I mean it'll have a t in it, not just x's and y's. No, okay, well that's the one that we'll be using on Monday. Okay, so if you want to prepare for Monday, you will dig out your first year notes, you'll find arc length, and you'll go through the derivation of the arc length formula, because that's going to be more valuable to you than the final formula you ended up with. Okay, so that's ArcLink. We'll jump into it on Monday with a splash.